Alright, session 2 is about sampling methods. There's two main groups. There's probability sampling and non-probability sampling methods. The probability sampling methods rely on probability theory, which means that members of a population have a known and random chance of being included in the sample. That's not the case with non-probability sampling. Now, of course, in order to calculate the exact probability to be selected in a sample, you need to know the exact size of the population, and that's just simply not the case. In very large populations especially, it's impossible to know the exact size of the population, so in those cases, non-probability sampling is more often used. Let's start with the first type of probability sampling method, simple random sampling. Simple random sampling is sometimes called SRS, and you can calculate the probability of selection for each unit by dividing the sample size by the population size. So in this way, probability of being selected is equal for all members of the population. Totally happens at random. So let's say, for example, you have a population of 100,000 people and a sample of 1,000 people, then 1,000 divided by 100,000 means that each unit has 1% chance to be included in the sample. Simple as that. One example of simple random sampling is random device methods. Random device methods are when you use any type of device. Could be as simple as flipping a coin or roulette in a casino or lotteries to understand or to calculate the chance each unit has of being selected in a sample. Let's say, for example, I put all names of all my students in a box or in an envelope, shake it well, and then let someone pick out a few names. If there's 30 students in class and I take out, or someone takes out 10 names out of these 30 students or 30 names in a class or in the envelope, then you know that each student has 1 out of 3 chance of being selected into the sample, or basically being drawn out of the envelope. So this is a very easy way to understand simple random sampling. Random numbers method is also sometimes used. That's when there's too many people in the population and a device can no longer be useful. In that case, a computer draws random numbers from a huge population at random. The benefit of simple random sampling is that selection is known and equal, so you know, in theory at least, how much chance each unit has of being selected in the sample. This way you'll always have a valid representation of the population. Now, of course, I make the side note that this is only theoretically true, because in reality, if you don't know the exact size of the population, you cannot use that formula accurately, so you cannot calculate the exact chance or probability of selection. But theoretically you could. And this is immediately also the downside of simple random sampling, is that you don't know the exact size of the population. You cannot account for everyone in the population, but you need it. You need a complete accounting of the population in order to calculate the chance of selection. So this is what I mean with sample frame error, which we talked about in the previous session. It's nearly impossible to have a complete accounting of the population. The closest thing you can get is a sample frame, which of course comes with sample frame error. Another practical application for simple random sampling is random digit dialing, which is usually used for telephone surveys. In that case, a list of telephone numbers is generated, usually when a company has all their clients' telephone numbers in databases, and then at random a couple numbers are selected, which are then called for interviews. The second type of probability sampling is systematic sampling, and systematic sampling used to be more popular than simple random sampling because it's more efficient, but now with computer technology, simple random sampling has actually become more common. Systematic sampling is easier to use when you don't have data in an electronic format, and it all relies on a skip interval. So basically, from a directory or a list, which you know is called a sample frame, you can determine the chance that each unit has of being selected in the population based on a skip interval. And that skip interval is the population list size divided by the sample size. As you can see in the visualization on the right, every third person in the population is included in the sample. So that's what that skip interval refers to. This could be every third person, as in the example on the right, but could also be every 10th or every 205th name from a list that gets picked and gets included into the sample. So you might be wondering, wait, this is very systematic, right? How is this then a probability sampling method? So why do we include it under the umbrella of probability sampling? right? Because it's so systematic. You systematically pick the third person or the fifth person or the however manyth person from a population and include them in a sample. Well, it's the starting point of the skip interval that is completely random, and that's why we still call this a probability sampling method, simply because the starting point is random. So the benefit of systematic sampling is again that you have a known and equal chance of selection for each unit because the random starting point. It's still more efficient than simple random sampling when you have no digital format. Now the downside is that, as with any probability sampling method, you technically need a complete accounting of the population, which is not possible, so you'll always have sample frame error. The next type of probability sampling method is cluster sampling, and cluster sampling is actually a fun one. With cluster sampling, the population is divided into subgroups, which we call clusters, and each cluster in itself is representative of the population. One common application of cluster sampling is area sampling, where you choose one specific area, let's say a city or a county or a neighborhood, and let that serve as a representative sample in and of itself of the whole population. So if one county or one neighborhood basically speaks for the whole population. Now you can already guess that there are some issues or potential issues with this. If one county or one city is not representative of the population, then obviously you cannot just pick that one city or county and use it as the cluster. This is called cluster specification error, which I'll also elaborate on one of the next slides. There's two types of cluster sampling, one-step cluster sampling or two-step cluster sampling. One-step cluster sampling means that from the whole population, you select one cluster at random and that's your sample. Now, of course, this, like I said, only works if all clusters are sufficiently identical. So in other words, if it makes sense to pick only one cluster, so one city or one town to serve as the sample for your whole population. Two-step cluster sampling is a little more complex, but also a lot more robust. So with two-step cluster sampling, you randomly select several clusters from the population, and then out of those clusters, you randomly select units. This is a good way to visualize it. Let's say this is your population and you have several different clusters in your population. So each of these little circles represents clusters in your population and you want to draw a sample from them. One-step cluster sampling means that you take one cluster and that becomes your sample, right? Now, of course, you can only do this if each of your clusters looks identical or almost identical to one another, if each of them is in and of itself a representation of the population. With two-step cluster sampling, you will select several clusters from your population, and then out of those clusters, you will randomly select individual units to include in your sample. So it's definitely a bit of a detour, but makes your sampling method more robust. The benefit of cluster sampling is that it's much more economically efficient, faster, cheaper than simple random sampling. The downside is that you still need a complete accounting of the population, so you need some sort of master list or register with every unit of the population, so you'll always have some sample frame error, which is the case with any probability sampling method. But in addition, there's that caveat of a cluster specification error. So there's always the possibility that clusters are just too different from one another, so that you cannot take one cluster and let it serve as a representative sample for the whole population. So the more different the clusters are, the less precise your sample results will be. If you were to do area sampling and use one area as the cluster or the sample for the whole US population, then obviously you couldn't take either Beverly Hills or Skid Row, because neither of those is representative of the US population. They're just too different. The last type of probability sampling method is called stratified sampling. And stratified sampling looks a little bit like cluster sampling, but it's actually very different. So let me explain differences. So with stratified sampling, you also create subgroups in a population, just as you do with cluster sampling. So you have a whole population and you divide it up in subgroups. Now, the difference is that with all the previous methods that we discussed, so simple random sampling, systematic sampling, and cluster sampling, you assume normal distribution of certain characteristics in your population. With stratified sampling, that's not the case. So with stratified sampling, you can work with unique subgroups subgroups that have characteristics that are not normally distributed in the population. So basically, with stratified sampling, you can work with skewed populations. Think of, for example, drug use in the US population. If you think of the characteristic drug use in the US population, that's not going to be normally distributed. That's going to differ very strongly based on certain subgroups. Think of, for example, college students, 50-plus housewives, babies, straight edgers, punks, and so on. So for each of these subgroups, drug use is going to be vastly different. College students might have pretty high drug use versus housewives. Well, actually, they might have some too. Babies will probably have close to zero drug use of any drugs, really. Straight edgers obviously don't use any drugs because they're straight edge, and then punks and so on. So it will differ a lot based on subgroup. Or another example where you have a skewed population is think of caloric intake among different subgroups of the population. If you compare bodybuilders who take in a lot of calories every day versus models or people who are suffering from certain illnesses, or the elderly population who take in a lot less calories, right? So in those cases, you have caloric intake being very different across different subgroups. So you can't just throw them all in one basket or expect one subgroup to speak for the whole population because they are so different. So this is exactly how the differences between strata or different subgroups in stratified sampling and clusters, which are the subgroups in cluster sampling, can be visualized. So strata on the left consist of different subgroups that are different from one another. Each stratum is very different from each other stratum. People within one stratum look like each other. So you have a bunch of green people, blue people, yellow people. So each group is very different from other groups, but they're very similar within the same group. Clusters are in and of themselves very diverse. They are, if you will, mini representations of the population. So this is why they are suitable for cluster sampling. You could pick one cluster and have it serve as a representative sample of the population, whereas with strata, you could not do that. So there's two different types of stratified sampling: proportionate stratified sampling and disproportionate stratified sampling. Proportionate stratified sampling means that you sample certain units from each stratum in a proportionate way to the size of that stratum in the population. So you respect the proportions in the population. Disproportionate stratified sampling is when you don't respect those proportions, but you have a good reason for that, if you do that because of variance differences. This is a way to visualize it. If you have your population on the left consisting of 4 different subgroups who are very different from one another, then you could use proportionate stratified sampling by making sure that the proportions in your sample are equal to those proportions in the population. So if there's a lot of those people in the pink triangle, you want to have a bigger representation of people in that pink triangle also in your sample. Whereas if there's a smaller representation of people in that purple field, you're going to have less units of that purple field in your sample. So you completely respect the proportions of those different strata in the population when it comes to your sample. Disproportionate stratified sampling means that you intentionally disrespect these proportions. So as you can see, the triangle people, the pink triangle, is not represented much at all. So you have a very small sample of those people in the pink triangle, even though in the population they form the majority. Whereas the purple people, even though they're a very small subset of the population, are very represented in a sample. So this is disproportionate stratified sampling. So why would you really do disproportionate stratified sampling? That's because of variability or variance differences. But what is that exactly? What is variability? Variability means that results are very spread out. So if you have research results on a certain characteristic that are very spread out in a group, in a population, we talk about high variability. Think of, for example, San Diego weather versus Sedona weather. I don't know if many of you have been in Sedona, Arizona already. It's beautiful, but the temperatures tend to be very different in the winter versus the summer, at day versus night. So there's more extremes. So as you can tell from the average temperatures on the left for San Diego and the average temperature for Sedona on the right, they're very close right? The averages are very close. However, the distribution or the extremes are much further apart. The highs and lows are much more extreme in Sedona versus in San Diego, where the variability is much smaller. So the differences are much closer together or much smaller. So this is a way to illustrate that idea of variability. I have another example for you in case you're not really into the weather forecast. Let's say your research question is, to what extent do you value or do students value their college degree? So we could expect that agreement in terms of how much value there is to your college degree would go up as class standing goes up. So I would expect that seniors would tend to agree more about the fact that there's value to their college degree because they've already been through all these classes, they're close to graduation, so they probably see more value in their college degree. Whereas freshmen probably will have less agreement among each other about how much value there is to their college degree. So in those cases, when you are dealing with variance differences, you need disproportionate stratified sampling to compensate for those variance differences. Look at the following chart. So we have freshmen's mean, sophomores' mean, juniors' mean, and seniors' mean. So we expect that seniors tend to have a higher expectation or a higher estimate of what the value is of their college degree. But in addition, we see that the graph or the curve for seniors is much more narrow. Seniors tend to be more on the same page with one another. Seniors tend to agree more with one another about the fact that there's value to their college degree. Whereas if you look at the curve for freshmen, you see that that curve is much more flattened out, much more spread out, because freshmen tend to agree less with one another. Some freshmen might be thinking, oh, there's a good amount of value to my college degree. Some might not know that at all or not feel that way at all. So not only do the means go up, we also notice that there becomes less variance as classifications go up. Now, in situations like these, you need disproportionate stratified sampling to allow for those variance differences. You need more sample size, you need to collect more units when there's more variance, and you need less sample size, or you basically need to collect less units when there is less variance, so that overall for the same sample size you achieve more precision. The positive side about stratified sampling is that you can use stratified sampling for skewed populations. Disproportionate stratified sampling is great to achieve more accuracy for the same overall sample size. So that's something you cannot achieve with any of the other probability sampling methods because they don't work on skewed populations. The downside is that you need a complete accounting of the population again, as always with probability sampling. And with disproportionate stratified sampling, it becomes a lot more complex because you have a different sample size, so a different N for each stratum.